Welcome back for part 2 of examining probabilities in this particular example where we had that we were doing in part 1 and from before when we were talking about just Venn diagrams. If all social media users monthly consist of, and we're looking at particular groups that are using Facebook or Instagram or TikTok. Notice that we had this group here in the corner. If all social media users added up to 3.8 billion, then 0.58 would represent those who are social media users but using neither Facebook, Instagram, or TikTok. So remember, this number inside the rectangle represents cardinality of kind of a different set, which is also a subset of this universal set. Okay, so there are two different numbers there. Anyway, so we had that Venn diagram that was of cardinalities. Well, we can turn it into a Venn diagram of probabilities by simply using this rule, which you can't see because there. No, you can't see that thing. Okay, so the rule is that a probability of an event is the number of things in the event divided by the number of things in the whole sample space, right? So using that on each of those numbers, for example, the probability that a social media user would be in this group that has only 1.97 billion users. Those are the people using Facebook, but neither Instagram nor TikTok. That probability is found by taking 1.97 and dividing it by 3.8 to get this number here, 0.5184. Okay, so transforming all these cardinalities of sets into probabilities simply by using that rule. Okay, so well, given that rule, that definition of probability, we have following rules must be true. So I'm going to go over the rules and also give some examples of using them in this particular scenario. So first of all, if you're always taking a subset of a larger set, the cardinality of that divided by the cardinality of that number always has to be less than or equal to 1. Because remember, the event is a subset of the entire space, sample space. Notice also that you could have the probability of an event being equal to 1, but in introductory statistics, we assume if that's the case, if the probability of event E is equal to 1, that it has to be the case that E must happen. No other possibilities. Also, the probability of an event could be equal to 0. And in introductory statistics, that we assume means that if the probability of the event E is equal to 0, that E cannot happen. So you can use that to check if you're ever making such statements about these ending values. Make sure that that makes sense when you translate it into English. Some other rules. The probability of the complement of an event is 1 minus the probability of the event. Let's look at an example of why that would be true. Well, rule number 1 about the definition that the probability has to be some number less than 1 is illustrated by asking, hey, what's the probability that a social media user randomly chosen is in category B? Which, if you remember, it was this one here, Instagram. I don't know why I had a C there, sorry. Instagram relabeling as being the set B, for Venn diagram familiarity. So what's the probability of a randomly chosen social media user being an Instagram user? Well, it's the number of Instagram users over the total number of social media users, and that was 0.2632. Where did that 1.0 billion come from? If you recall, in the previous video, we had some statistics like that helped you fill in all the blanks on this entire Venn diagram, right? Maybe that was 2 videos ago. And so I'm just using that here. So the probability of B is 0.2632. Well, then the probability of B complement is easy enough to find using rule 3. The probability of B complement will just be the number of things in B complement over the number of things in S. I'm explaining kind of like why the rule is the way it is. Why is this rule 3 here? That the probability of B complement is equal to this. Why is that? Well, just going by the definition of probability, right? The probability of an event, B complement, is the number of things in B complement over the number of things in the total space. If you were trying to count up the number of things in B complement, I mean, look at it, you'd be over here saying, well, the number of things in all of S would be everything, all these numbers I see here. All these numbers inside the rectangle would have to add up to this one. But if I want the things not in B, well, I could take this number and subtract away the ones that aren't in B, right? Similarly, I could take, to find the number of things in B complement, I could take the number of things in S and subtract the number of things in B, right? So by algebra, that gives me number of things in the space over itself. That's a difference. That's how fractions work, right? If they have a common denominator, if this has a common denominator, the subtraction here, it can be split up into a difference of fractions with the same denominator. That's a mouthful, sorry about that. And number of things in the space over itself, well, that's just 3.8 over 3.8, which is just 1. And number of things in B over the number of things in S, well, that's the definition of the probability. So the probability of the complement is 1 minus the probability of the original event, and that would give us 0.7368. So that's an example of using rule 3, but also a little explanation of why the rule is. Can't resist. Always want to tell you why. So let's see. Third rule. Back over here, the third rule. Third rule is that the probability of a union of 2 events is equal to the sum of the probabilities of each one minus the probability of their intersection. Why is this called the addition rule? Well, let's look at an example of finding that right over here. Okay. Make sure this thing doesn't take a dive again. Uh-oh. Looks like it's gonna. All right. Okay, so an example of that addition rule. Is there it is. There, you took a dive. Sorry about that. Right. Okay, so the probability of the union of 2 events. What are the 2 events here? B and C. B is the set of all Instagram users, and C was the set of all TikTok users. So what's the probability that a social media user is either an Instagram user or a TikTok user? That's how you would translate that into English. That would be equal to the number of things in B union C. So union, I tell my students, think of as kind of like a bowl where you just throw in everything in B and back over here where we're counting things, everything that's in B, all those users, everything that's in C, put it in one bowl, right? Well, the number of things in that bowl is equal to the number of things in B plus all those that are in C Now notice that I just counted this group and this intersection here twice. Counted it once here, counted it a second time there. So I've got to take one of those counts away because I've just counted that group twice. So I subtract the number of things in the intersection. What does that give us? Well, that gives us let's see, that's number of things I've got there, so I think I need to fix some numbers, right? So the number of things in B, oh yeah, that's right, number of things in B, excuse me, I don't have to fix numbers, I have to just remember that I have those numbers up there to work with, right? The number of things in B, there were 1.0 billion of them, remember those, that's Instagram users. The number of things in C was 0.8 billion, and the number of, that's TikTok users, and the number of Instagram and TikTok users that was given to us. We used that. We had that 0.55 billion. So back over here, I was able to just put those numbers in and get 1.0 plus 0.8 minus 0.55, all divided by 3.8, giving us a probability. 0.3289, that's the probability of, you randomly pick a social media user, what's the probability that they use either Instagram or TikTok, okay? I want to point out that each of these probabilities also could be written as a percentage. Remember the rules of using percentages. This is the same thing as if I move this 2 decimal places over and finish it with a percent symbol. Then another way people phrase this in English is that of all social media users, 32.89% of them use either Instagram or TikTok. Okay. Another way people phrase this, since that was a probability and that's equal to this percentage, people will say, what's the percent chance that if I randomly pick a social media user, I'm going to get somebody who uses either Instagram or TikTok? Either or is associated with that symbol, the union, right? So the chance, percent chance, we'll say, is 32.89%. So you have to be practiced enough with interpreting the English so that you can go backwards or forwards, either interpretation. But mathematically, that decimal equals that percentage is exactly true. Okay. So, what's another rule? Oh, sorry. And so actually, did I use the rule here? I kind of explained again why the rule, I could have done it this way. So the probability of B union C, I could have done it this way. It's the probability of B plus the probability of C minus the probability of their intersection, right? And if you just break up this expression here, you have 1 over 3.8, that's this probability, 0.8 over 3.8, that's probability, minus 0.55 over 3.8, that's the probability of their intersection. So you can go ahead and just use that rule if you have those probabilities already worked out. Or we could have done it this way. That's another thing. So often with these questions, there's a couple of different ways you can do a problem. If the book's answer looks like it's just doing it one way, but you are legitimately using the rules and you're getting the same number, then that's probably okay. Let's look at another set of these rules and examples of using them. Let's see. Rule number 4, right here. The way probabilities work is that if A and B, now remember these are events, which are subsets of the sample space, of the set of all possible outcomes. If this event and that event are disjoint events, what do we mean by that? If their intersection is empty, right? Then the probability of both events occurring of you're saying event A and event B are occurring, the probability is equal to 0. Why? Because that's equal to the number of things in A intersection B, which is the number of things in the empty set, right, over the number of things in the whole space. If that's equal to 0 over the number of things in the whole space, yeah, of course that's going to equal to 0. And it should be true that if you have a bunch of disjoint sets, the sum of all their probabilities should be equal to 1. You could say we have an illustration of that if we have a filled out Venn diagram like this one here. Look at all these disjoint events because we have found the probabilities of each one of these events that are disjoint from all the others. If you take all these probabilities and sum them up, you should get 1. Okay. Finally, we have a very handy property that your book is not giving you guys, and I don't know why that is, but I'm going to throw it in there. And that is using something called De Morgan's rules. It says that if you're talking about the complement of the union of a set, that's the same thing as the intersection of their complements. Look how that works notationally. Let's see if I can move this so you can for sure see this. Yeah, right, okay. Don't know why it's so tippy. Right, that's a bit of a weird angle, sorry. So notice that it looks like you're just taking the complement and distributing it through there. So you find the complement of this, you invert that union symbol into an intersection and the complement of B. So everything gets changed, flipped. There's another rule that says that the complement of the intersection is equal to the union of their complements. Again, it's kind of like you're distributing that complement symbol through there, changing every symbol. The intersection flipped to a union. Let me show you an example of using that. Suppose in the wording of a problem about this example, they are asking you to find the probability of A complement union B complement. I'll talk about the wording of that in a second. How you would phrase that in English using this social media users problem. But right now, let's just talk about applying this trick of De Morgan's rules. The probability of the complement of A union B is really what they're asking, because that set is equal to this set. So if I'm finding the probability of this event, it's the same thing as probability of finding that event. And what are we using there? You could just say by De Morgan's. That's kind of shorthand for De Morgan's. Well, that's a complementary event. By the rule of complementation, rule number 2 over there, that's equal to 1 minus the probability of A union B. What was the probability of A union B? We worked that out, didn't we? Oh, we could have. Oh, I know what happened. Let's say that instead my example is this one, that I'm finding the probability of involving the B union C. So let's see, what would be, what if I wanted the probability of B complement intersection C complement? Yeah, sorry. I switched my examples midway. So that's the same thing as finding the probability of, what's equivalent to that? The complement of their union. Right? Haven't found the probability yet. I'm just saying, look, that's the same as that by De Morgan's. Okay? All right, now, what is that? Well, by the complementation rule, that's 1 minus the probability of B union C. And that's the probability we already found here on the board. Down here, the probability of B union C, if you remember, was 0.3289. 0.3289. And what is that? Using your handy dandy calculator. 1 minus 0.3289 is 0.6711. If you remember when we were down here, we had a little approximation symbol here at some point, right? It was approximately 0.3289. So right in there is when we'll use that same approximation. And so we have the probability of B complement intersection C complement is the same thing, is equal to approximately equal to 0.6711. Maybe you noticed I've been taking all these, rounding them to 4 decimal places. I found with this book and with my math lab, if I just always do that, then I can, if they ask for only 3, I'm okay. If they only ask for 2, I'm okay. If they happen to ask for 4, I'm all ready. Okay, so get used to rounding them to the nearest 4th decimal place. I think that seems to work well. Okay, now let's talk about the English. How in the world would they have asked that question in English? Well, let's see. B complement are all the things outside of B. So everything my hand's not covering up. C complement is everything my hand's not covering up here, right? What's in the intersection of those two? Well, that's if you take everything that my hands plural are covering up, and here's B union C, right? If I cover that up, what's left is B union C complement, right? So the probability of finding something that's in this part that I have not covered up is the same thing as 1 minus the probability of B union C itself, which we'd already found. Still didn't get to the English. Okay, so B, set of all Instagram users. C is the set of all TikTok users. So here they could be asking, if you randomly select a social media user, what's the probability that they are not an Instagram user and not a TikTok user? Yes, where you put that and how you phrase it. English is so ambiguous, it's very difficult. Which is probably why all this notation was developed, so we could zero in on exactly what we meant to say. Okay.